Okay, so announcement, quiz number 3 will be Thursday, 2/7/13, so tomorrow. It's going to cover 1.5 and 1.6. So if you could do the Wiley questions and the written homework questions on that, if you've done that, you should be in pretty good shape for the quiz. Written homework 1.1 to 2.1 is due Friday, so I give you that little extra time to turn it in by 5 o'clock, my office door, 307E of Mannheim. So there will be envelopes that you just slide it in. Last time, someone wanted to see an example with 1 minus cosine of 3x or 3h to see how that works. So I'd look in the book, randomly pick 36, and then wasn't exactly what I intended it to be. So it turns out this problem's more complicated than originally anticipated. It's not that bad. You just have to know where you need to go. So I had to play with it for a few minutes to figure out, okay, this is not what I originally thought it was going to end up being. So if I divide top and bottom, if I factor this out, it's still 0 over 0, and I don't get anywhere. So I really need to get it into a form that I can manipulate. So this being squared, cosine squared 5h minus 1, it is a perfect square. I could factor it. That doesn't get me anywhere either because it's still 0 on bottom. So I think of my trig identities, because sine's almost a little easier to deal with because all I have to do with, if I had sine of 5h, is divide top and bottom by 5h. And then I could say that limit as h goes to 0, that goes to 1. So by doing this, I'm going to multiply top and bottom by 1 plus cosine of 3h. And then when I do that, I'm going to rewrite this as minus sine squared of 5h. So if I write sine squared x plus cosine squared x equals 1, then I have sine squared x equals 1 minus cosine squared x. So if I multiply both sides by -1, I get minus sine squared x equals cosine squared x minus 1, which is what I have there. So I can rewrite that. Does everyone at least believe that to be true? Maybe not ever come up with that on your own, but could say, okay, these two things are equivalent, so I can replace it with a different representation. I'm just manipulating that identity to get it into something that I can evaluate, because what I did before wasn't getting me anywhere. So when I do this multiplication, I have the limit as h goes to 0. I have 1 minus cosine squared of 3h over sine squared of 5h times the quantity 1 plus cosine of 3h. I like to deal with sine instead of cosine, so again, I can rewrite this. This time, this would just be sine squared of 3h. Yes, there's a negative there. Thank you. Drop that negative.
So it wouldn't be 9h squared. You don't multiply 3 into h.
No. You wouldn't. It's cosine of an angle. So if you think of cosine of theta times cosine of theta is cosine squared theta, not cosine squared of theta squared. Yeah. But this is just an input, so you don't square that. Okay, so now rewriting this, I have the limit as h goes to 0 of sine squared of 3h over minus sine squared of 5h times 1 plus cosine of 3h. Just kind of testing myself here when I plug in 0. Cosine 0 is 1, so 1 plus 1, I don't have any issues. So I don't have to worry about canceling that out. And I need to know how to deal with this sine. Sine squared of 3h divided by sine squared of 5h. I could rewrite that as sine of 3h divided by sine of 5h quantity squared. Right? If I have a squared over b squared, I could write that as a over b squared. If I do that, I have the limit as h goes to 0. I'm going to pull this negative I'll just leave it for a minute. So I have sine of 3h over sine of 5h quantity squared, but the negative's outside of that. 1 over 1 plus cosine of 3h. Now I can use the trick, divide top and bottom of the numerator by 3h and top and bottom of the denominator by 5h, right? So I didn't leave myself too much room, but let's see if I can squeeze this in here. 3h, and put a 3h up here, because it has to be within those parentheses. So here I have a 5h, so I have a 5h here. I can do that because it's only 1, just in the form 3h over 3h. So now I know that this goes to 1, and this goes to 1. So I'm left with the limit as h goes to 0 of 3h over 5h quantity squared with a negative out front times 1 over 1 plus cosine of 3h. Now I can simplify the h's and plug in what I have. So I have minus 3 over 5, this quantity squared, times 1 over 2. I have minus 9 over 25 times 1 over 2, which gives me minus 9 over 50. A little bit more difficult problem than I originally intended. So that's the danger of me just randomly pulling out questions, thinking it's going to end up one way when it turns out to be quite a bit more complicated. Because I plugged in the limit as h goes to 0, cosine of 0 is 1, so this becomes 1 over 2. And honestly, the only calculus part is when I plug h goes to 0. Everything else is manipulation, trig, and algebra. And knowing the fact of the squeeze theorem, this is going to simplify to 1. What? This? In front of it? This 3? Where did it come from? Cosine of 3 times 0. Cosine of 3 times 0 is cosine of 0. If I plug in h goes to 0, I have cosine of 3 times 0, which is 0. Question? No. No. So yeah, you can breathe now, right? These are complicated ones. Question?
So the 1 plus cosine 3h goes to 2 because cosine should go into 0 is 1.
Yes.
And then 1 plus 1 is 2.
Yes.
Sorry.
So if you can follow it, that's great. If you can, I wouldn't expect you to pull this out of thin air. So, I mean, I didn't pull it out of thin air yesterday. In 2 seconds, I looked at it. So, I mean, you wouldn't have this on an exam. So, but you can see the applications of the sine of 3x or the sine of 3h and how to manipulate it to go to 1. You might have that type of problem on there when you need to manipulate it in a form, but never where you pull it out of something like this. But being exposed to techniques like this, or being exposed that you can get there if you hit it hard enough with a hammer, you might start one way, get nowhere, and say, okay, I need to look at it a different way. Let's try to write it in sine. Especially with trig. If you write it in terms of sines, maybe it'll simplify. If you do that and 2 pages later find out it doesn't get you anywhere, start fresh. If you have the time to spend on the problem, which in higher level classes, you might need to apply something like this, and your basis of calculus is going to come up and be important. Like here, the base of trig in college algebra came in very handy, where when you're learning trig in college algebra, you're never really going to think you're going to use it in this way. So the same thing if you get into higher level engineering courses or higher level biomath courses or bio courses, you might need to evaluate some kind of limit as, something goes to a certain value, and it might be like, oh, let's just try this technique and it works. So, I don't know. Even though this won't be on this exam, it's not lost knowledge. It might come up later on. Okay, so last time we talked about 2.1, and we spent time with the average rate of change and the instantaneous rate of change, right? let me pull up our notes from last time, just kind of give us a base of what we're going to talk about. I don't know where I grabbed them at.
Does the squeeze theorem only work if you go to zero?
Yes.
Okay.
No, sorry. No, it doesn't.
Okay.
The squeeze theorem only works if you can bound a function by two other functions. But if you said as it was going to 5, as long as you have that other function going to the same thing on both ends,
Okay.
the left-hand side and the right-hand side, and you have that middle function bound by that, it doesn't have to be 0. But the limit as h goes to 0 of sine of x over x is 1. But if you look at the limit as x goes to pi over 2 of sine of x over x, you would plug sine of pi over 2 over pi over 2. Does that make sense? Which would then just be 1 over pi over 2, so 2 over pi.
Okay.
So you would plug that in. You wouldn't need the squeeze theorem for that. Does that make sense?
Yeah.
Okay. Okay, so 2.2, or sorry, 2.1, we spent some time on looking at what is the slope at the various points. So 2.2 is the derivative. From 2.1, we had the instantaneous rate of change at x equals x naught. So the slope of that was the limit as x goes to 0 of f of x naught plus h minus f of x naught over h. Right? You guys remember doing that? We plug in point 2. So we'd have 2 plus h minus f of 2 over h, and take the limit as h goes to 0. In 2.2, so this is 2.2.1, this is the definition of a derivative. And it turns out we use the notation f prime of x. This is going to be the limit as x goes to 0, or sorry, h goes to 0 of f of x plus h minus f of x over h. So this is at point x. So here you can see why we favored this representation of the slope at a point. Because we had 3 of them, right? We had the limit as x goes to x naught, or x1 goes to x naught. And they had those different representations, if you recall. So just to take a minute, and in 2.1, we had the representation here as x approaches x naught, the representation, and then in the denominator you see we have x minus x naught. And as x approaches x naught, this goes to 0. So then we said, okay, let's call that h. We'll let h equal x minus x naught, and take the limit as h goes to 0. So you can see here, we have the difference of the slope of the secant line and the slope of the tangent line. This representation, the slope of the tangent line. The slope of the secant line is just the change in y over the change in x, which has nothing to do with the limit. It's just going to be a number. You guys have done that in college algebra. Find the average rate of change between point A and B. That's f of b minus f of a over b minus a. We could think about it as a function of time. And a lot of times in physics, we talk about functions being a function of time. So we could replace x's with t's, and we'll do some examples later on once we get the understanding of what's going on. X is just a variable. It can be replaced with any other variable. The important thing is h is going to 0. We talked about the instantaneous rate of change and the average rate of change, the difference. You see the average rate of change, there's no limit out front. You take the change in y over the change in x. So if I look back up this graph here, The change in y is going to be f of x naught plus h. That's my y value of my point 1, minus the y value of point 0, which is just going to be f of x naught. So change in y over the change in x, which would be x naught plus h minus x naught, which would just be h. Right? Okay. This brings us to question.
Is it always as h approaches 0?
Correct. Because what h represents is the distance between the 2 points. Because the whole application of this tangent line is saying, does that make sense? So
Yeah,
I have this,
just at
yeah,
that.
yeah, I have this secant line, and I can calculate, not using calculus, change in y over the change in x. But what if the change in x was 0? And we don't have a way to do that unless we take the limit. So I'm approaching this point. So I'm going to call this distance h, and I want to take it as h approaches 0.
It gives you like I don't know what word it is, but it gives you something to like compare to for a difference. Or
Yes, and so the reason why this equation is so more favored over this equation is because you already have that h in the denominator. You only have to factor one term. But here, you have to actually factor out an x minus x naught from the numerator to cancel that. Do you guys remember doing that one on Wiley when they had you do the difference quotient, and then they had you do one with like w and x? And you had to factor out that w minus x, which then you had to end up factor by grouping. And you had an x squared minus w squared, and you had to use the difference of squares there. So if you remember doing that one, it was kind of more algebraically intensive. So what, a long time ago, they decided, okay, let's not use, this term's always going to be going to 0, right? If I have x going to 5, then I have x minus 5, and if x is going to 5, then that goes to 0. So let's just call that h. And then we only have to worry about factoring out an h in the numerator. Today, you'll kind of confirm that h is a lot easier to deal with than x minus 5 or x minus 2 or x minus whatever the number would be. We're just going to call that h, and h is going to go to 0. The distance between 2 points goes to 0. Okay, so just to kind of reiterate, the definition of the derivative, oops, try to zoom in too much there. The definition of the derivative, so this notation, f prime of x, that is denoted as a derivative of a function. This is the derivative of function f with respect to x. You could also have the derivative with respect to t, with respect to any variable. The way we find the derivative is by applying this limit of this difference quotient, which we've manipulated difference quotients before, right? You did that on your first quiz with x squared. But now we're going to go one extra step and apply the limit as h goes to 0. So any terms left with an h in it is going to go to 0. So I think the best approach in this section is just to do some examples. So we did example of x squared yesterday, right? So let's just do one a little bit higher level. And so this is example. Let's take our function is x cubed minus x. And we're asked to find f prime of x. This might be written out as find the derivative with respect to x. Or they might say find f prime of x. You need to understand what that means. That's saying finding the derivative. Next week, we're going to learn the power rule, which is a simple way to find derivatives. Some of you might already know that. You might already know what the derivative is. However, you need to show your work. If you look on Blackboard, there's copies of old final exams. Probably 95% of them have a problem on there worth 10 to 15 points that says use the definition of the derivative to calculate the derivative. Use the definition of the derivative to find the derivative of this function. If you just write the answer, you won't get any points. Matter of fact, a lot of times it tells you what the derivative is. So you just need to confirm that algebraically. Okay, so we learned that the definition of the derivative is the limit as h goes to 0 of f of x plus h minus f of x over h. So what is f of x plus h? If f of x is x cubed minus 3, f of x plus h is good. X plus h cubed minus x plus h. F of x would just be x cubed minus. Does anyone know what x plus h cubed is? Okay, think of the binomial theorem. So if you guys remember the binomial formula? Or Pascal's triangle? All right. It's not binomial. Yeah, it's binomial expansion or Pascal's triangle. This gives you the coefficients. So if I'm cubing something, I look here and that means it's x cubed plus 3x squared h plus 3xh squared plus h cubed. Right? You could cube it out yourself. If I have x plus h times x plus h times x plus h, I'm going to get the same thing here, right? If I square this term, I have x squared plus 2xh plus h squared. Then if I multiply it by x plus h again, I get what I have up there. So, I mean, if you really get stuck on it and you forget Pascal's triangle and you forget how to do it, you can do it in a relatively, a relatively short amount of time. I mean, it's not too long. So that's just the cubed part. If you're going to plug in f of x plus h, you also have to remember there's a minus x there. So just to kind of write this out, f of x plus h would be x cubed plus 3x squared h plus 3x h squared plus h cubed minus x plus h.
Right above that, where you have the x squared plus 2xh plus.
Yeah.
That line above that one, that's not dividing. That's just saying that becomes
Yeah,
that. Right?
I'm just saying this part becomes that. And yeah, sorry. So yeah, this part becomes that, and then I still need to multiply it again, which would then give me 6 terms. The terms would look like x cubed plus 2x squared h plus xh squared plus x squared h plus 2x squared h, or sorry, no, I already said that one. 2xh squared plus h cubed. Then you're going to have 2 terms that add up to this 3x squared h, and 2 terms that add up to this 3xh squared. You're going to get the same thing is what I'm trying to say here, but going about it maybe a little bit longer way. Question?
Where's the minus x plus h come from?
This minus x plus h, because I'm looking at the function, and everywhere I have a variable, I plug in x plus h. So, yeah, looking at the function, everywhere I have a variable, I plug in x plus h. X plus h squared is this part. So maybe I can kind of highlight this is x plus h cubed, and this is just x plus h. So the nice thing on these derivative functions, you will know your whole goal, the whole problem, is I have an h in my denominator. So my numerator has to simplify so I can pull out an h to cancel it. If that doesn't happen, I made an error algebraically. So if you would have accidentally forgot this term, you wouldn't have been able to cancel out an extra x. So you would know you have an error. So sometimes it's nice to give you that reassurance you're on the right track. Because if you get to a point where your numerator doesn't cancel, then your numerator, all the terms that don't have an h in it have to cancel. If they don't, you did something algebraically wrong in the previous step.
But you have to subtract another.
You do. So, so if I take here the limit as h goes to 0, I have this function, which is what I had here. I still have this other term to deal with. So I have x cubed plus 3x squared h plus 3xh squared plus h cubed minus x minus h minus the quantity x cubed minus x all over h. So just to kind of reiterate, all of this is f of x plus h. This is just f of x. All of your f of x should cancel. If it doesn't, something didn't go right. So you see here, this negative x cubed would cancel with this positive x cubed. This negative of a negative x would be positive x, and that would cancel with this minus x. So all the terms I have left have an h in it. So I'm all on the right track. Can you see how that can be a good way to check yourself? So now I need to pull out that h. The limit as h goes to 0. If I pull out the h on top, I'm left with 3x squared plus 3xh plus h squared minus 1 over h. Those cancel. Go ahead and write this extra step, which you wouldn't need to. So now I actually apply the limit, and the limit says h is going to 0. So any terms with an h in it goes to 0. So this term goes to 0, this term goes to 0, and I'm left with 3x squared minus 1. Fun stuff, right? That is the function that describes the slope at any point. So the slope at any point is defined as this function. So say, so what would be the slope at x equals 1?
Something more to the x.
Mm-hmm. 2, right? So here my slope would equal 2. So if I wanted the equation of the tangent line, I have the slope. So what would be my point at x equals 1? So slope is 2. My point would be 1 comma, what's my point? 1 comma 0. Very good. Because the point is on the graph. So you always look at, if you think of x comma f of x, the original function. So the equation of the tangent line would then be y minus 0 equals 2x minus 1. You can also write this y minus f of x equals f prime of x, x minus, what do I think of? So I'll say x1, because that, for the point x1 comma f of x1. What?
The f of x1. Yeah, why is it?
Because the original function is x cubed minus x. That original function. So if I plug in 1 to the original function, I get out 0. Right? So if I want to say, what's the point on this graph at x equals 1, the point would be 1 comma 0. The slope at x equals 1, I plug in 1 to my f prime of x and get 2. So later on, this formula will come up in your book using this notation that the slope at any point is the value of the derivative at that point. Question?
Where did you get the minus 1? Where did that come in?
This minus 1
In the slope.
here? Because this is the expression. When I factor out an h, I took an h out of this term, so I have 3x squared. I took an h out of this term, so I have 3xh.
And then when you took the h out of the h,
I had minus 1.
Okay. I get it now.
Good. Does anyone have any question where I got this point from? Okay, this point, anytime you need an equation to a line, you need a point and a slope. So the point is from the original graph, the original function, right? This function, so let's graph this function real quick, and it might make a little bit more sense here.
You just plugged 1 into it, though.
Yes.
So you could have plugged 47 into it, as long as your point was 47.
Yeah, then I would be talking about the equation of the tangent line at the point x equals 47.
Right.
So then my y component would be 47 cubed minus 47. But my slope would be 3 times 47 squared minus 1. Okay? The slope has to do with the derivative. The point has to do with the original function. Question?
The only part I'm getting lost on
Mm-hmm.
is f of x plus h, where you basically have
This?
to plug down a little bit into your right, where you have a thread about there, a little bit down lower. What is that right now mathematically as like right before that step?
So here? Or
It would be like, what do you write out like to plug in for that, the x cubed plus or minus x, and for x dealing with that h? Are you like multiplying those together?
I'm subtracting them. I'm taking this expression minus the quantity of this expression.
But how do you get that expression?
X equals h.
The first expression or the second one?
All of it.
Okay, so okay, this f of x plus h is a placeholder. Yeah. So f of x plus h, I'm going to replace that what that represents as a function, which would be all of this, right? But to find that, I plug in x plus h to my original function. So I have x plus h cubed minus x plus h. Well, x plus h cubed is this expression.
Well, does that other minus x just disappear? Or my
Here,
question is, why do you separate?
I want to emphasize that I'm subtracting the quantity x plus h. So I need to distribute that negative. That's kind of why I have a parenthesis here. Because this is my first term, x plus h cubed. This is my second term, just x plus h. But I need to emphasize that that negative is being distributed. Because if I don't distribute it, then I end up with 3x squared plus 1, which is not correct.
I guess what I was thinking is that you would take the x cubed minus x and distribute that to the x, and then also distribute that also to the h. I was just confused why you would distribute x cubed to one part of it, and then take the minus h and distribute it to the h part.
Are you getting caught up on this x cubed minus h, why they can't, or this x cubed minus x?
No.
Okay, I'm sorry. I don't know if I'm... does anyone else have any questions on where this come from? The concept is what you need to basically memorize and know how to apply. Because all the problems will be just a little bit different. So you take f of x plus h minus f of x divided by h as h goes to 0. The whole goal of manipulating or simplifying the numerator is to cancel all the other terms that don't have an h in it. So then you can get to the point where you only have terms with h's in them. So you can factor out that extra h to cancel the h in the denominator. Once you've done that, you should be able to apply the limit. So any other remaining terms with an h in it goes away because the h goes to 0.
Can you slide it up just a little bit, please?
Oh, sorry. Yeah, I'm just trying to emphasize that you plug in your original function, you plug in x plus h. That might be quite a bit long expression. That might have quite a bit of terms. Minus the function. If the function has more than one terms, you need to be very careful distributing that negative throughout. So, I want to graph this function because I think seeing what's going on, it might be kind of beneficial. So if I take, so we did the work on the previous page to show that if I graph this function, it looks like, so this is x cubed minus x. If I graph the quadratic, this is a quadratic shifted down one. Turns out I have a function like this. This is 3x squared minus 1. So this is the derivative, and this is the function. Eventually, we'll get to where we're tying graphs of these two functions together. And if you think about it, the red function, which I don't know if it shows up to red on this, represents the value of the slope at any given point. So here you can see my slope is a positive number. So it's above the x-axis, right? The derivative is above the x-axis. If I keep going, my slope is decreasing, right? So if x stays the same, or if x is going this way, my slope is decreasing, and then at this point, my slope is 0. So you can see that the value of the derivative is 0 there. And then as soon as I get past this point, my slope becomes negative. It means my derivative is below the x-axis. You guys see that? Negative, 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 and it's getting larger negative, and then at some point, it starts going back to 0. So it's getting smaller. So at this point, it's back to 0. And then here, my slope is then all positive, right? So we're not quite there yet, but eventually that's where we're going to, is being able to pair graphs of functions with the graph of their derivative. So if you can say, okay, if this is the function, then the derivative has to be 0 at this point and this point, because the slope's 0 there. If I follow the tangent line, or if I follow the slope, 0 here and 0 here. So the value of the derivative at these 2 points have to be 0. Eventually, we're going to get there. Right now, we're just calculating the derivative. So let's look at an example, one more example. Yesterday, we did the example 2 over x. Do you guys remember doing that? Plugging in points. So today, let's look at let's say f of x equals 1 over x squared. Find f prime of x and f prime of minus 1. So you're going to have to deal with fractions and the difference quotient, but don't be intimidated by them. So we know the definition of the derivative is the limit as h goes to 0 of f of x plus h minus f of x over h. So what is f of x plus h? 1 over x plus h squared. And x plus h squared is x squared plus 2x. Yeah. So you can see how eventually, I mean, these concepts are like, you'll be doing the algebra enough that it's going to just be second nature. And you don't actually have to square the x plus h out if you want to leave it as x plus h. Good. Good. The setup's perfect. Now you need to simplify it because we want to cancel this h in the denominator. Okay. To do that, we need a common denominator in the numerator so then we can simplify it. Got the answer? Are you one of those people that... Ideally, I mean, it would be nice to, because then you could confirm you know what you're doing. And math is not a spectator sport, and it's almost a muscle memory type thing. If you do it enough, you can get that muscle memory, and it kind of helps with stress, anxiety. When you come take the exam, your hand will know what to do, almost, there won't be too much thinking about it. You'll have the process of doing it. So,
Right track there.
you can leave it like that, perfectly fine. You don't have to go that far, but if you do, you're on the right track, yeah. You're not on the wrong
I see
track.
what you mean. I can just leave
Yeah,
it like that.
you could just leave it like that.
Gotcha.
Because your only problem is with this h in the denominator. Your goal is to simplify the numerator to be able to pull out an h to cancel it. So the second denominator, the denominator of the fraction in the numerator, you can leave that alone because it's going to come out to be okay. Because you have an x plus h. And if h goes to 0, that goes to x. But here, if h goes to 0, it goes to 0, which is a problem. The common denominator is going to be this times this, right?
Right.
So leave your common denominator, go ahead as factored, as this times this. So what
Okay.
term does this mean?
Oh, that means that.
So be careful with that negative, because you need to make sure you distribute it. Close. Let me see what's going on. So your common denominator was this times this. You can't just do that.
Okay.
Yeah. Comment on fractions. 1 over a minus 1 over b does not equal 1 over a minus b. It equals b minus a over a times b. Common denominator, right? I can't just do this and cancel those x squareds. It's not going to get you anywhere. So if you did that, that tells me you can't even begin to attempt the calculus because the algebra is just wrong. I know you know the answer. Can you show the answer? Good. Okay, so can you cancel this and this?
Oh, okay,
Yes.
yes. This and this.
Mhm.
And then
If you pull out an h,
from the top.
mhm,
But then what's at the bottom?
which this is perfectly fine. If h goes to 0, this goes to
0
X-
times whatever.
this goes to 0 and this goes to 0, but you have x squared and x squared just goes to x to the fourth.
Okay.
It's not causing a problem. This h is causing a problem. So if you factor that out, you can cancel it. You're almost there.
So, okay.
Okay, so you pull out an h, right? And you cancel with this h, but you didn't get rid of it.
No, I haven't
Okay, there you go. So now you can cancel it.
used that.
So now plug in h goes to 0. What does your numerator go to?
2x.
What happened to the negative? But yeah, good. Yes.
X to the fourth.
Yes. And then simplify that.
Or x to the fifth.
Exactly. That's the correct answer. Good. Good. You're almost there too. If you distribute this negative, your x squareds cancel, right?
Yeah.
And then you can pull out an h to cancel that h, and then plug in everywhere else h goes to 0. You're really close as well. Don't worry about don't worry about this denominator because it's not causing you problems.
Okay.
If you plug in h equals 0, this goes to 0,
Okay.
but you still have x squared times x squared, which is x to the fourth, which isn't a problem.
Okay.
think I just heard you answering a question. But
Mm-hmm.
cancel that H out.
Mhm.
I still have an H.
That's
But
fine.
that's okay.
That's fine. Yes, you're so close to the right answer. Close. Pretty close. This -1 shouldn't be there. Here, this is an h squared, right? This. So if you multiply top and bottom here, you end up with x squared minus 2xh minus h squared. So this is an h. This is an h, and this is an h.
Oh, okay.
You're really, yeah, but just that one.
Like, there's something in the middle and like not because this is
Okay, so good. Good. So these x squareds cancel, right? So then what's your next? You would have.
So I'm not sure how to write it down here after I go from here.
So your denominator here. Okay, so you found common denominator, right? So you can write x squared minus all of this over the common denominator. You don't have to write it in two expressions.
Oh yeah, I could do that. So here, don't I multiply this side by x squared over x squared?
Which you did.
Okay, yeah.
You did, which you got an x squared, yeah.
Okay.
Yeah, okay, I'm going to write this out. So
Because these two divided by this, you can move this to there.
you can. Okay, so I'm going to go over this. Okay. Okay, so let's look at what we have here.
End up with -2.
Limit as h goes to 0 of 1 over x plus h squared minus 1 over x squared over h. If I look at where my problem lies, it lies in this h being in the denominator. So I need to cancel that. Anything else I do, I'm okay with. I'm okay leaving it. I'm okay factoring it. I'm okay expanding it. You're going to get to the same answer. So here I need a common denominator. So I have the limit as h goes to 0, x squared minus the quantity x plus h squared all over x squared x plus h quantity squared over h. Does anyone have any questions at this step? I found that common denominator. If you would have expanded it and then wrote it, it's perfectly fine. I'm eventually going to expand the one in the numerator because I need to simplify that. Right? Because I have to, because I need to cancel out this x squared. And I'm guaranteed that by approaching it this way, I'm going to be able to cancel out that x squared. So if I write the limit as h goes to 0, I have x squared minus x squared plus 2xh plus h squared over x squared times x plus h squared divided by h. I can leave this h in the denominator, or I can flip and multiply it, and then it would be pulled up to the denominator of the fraction in the numerator. It's a style thing. You're not wrong to leave it this way. Because eventually if I have an h out front, I can cancel it. So I'm going to leave it like this. In this expression, I'm going to leave it like this. In the next expression, I'm going to pull it up in the numerator. So the x squareds cancel. You be very careful with this negative because it's being distributed. So I'm left with a minus 2xh minus h squared. And then my denominator is x squared times x plus h squared times h. So you see that? If I flip and multiply h over 1, 1 over h, so my h ends up in my denominator of my fraction in my numerator. Okay, this h is giving me the problem. So factor out an h. I have minus 2x minus h over x squared, x plus h squared times h. And running out of time, the h's cancel. I'm left with minus 2x minus 0 over x squared, x plus 0 squared, which gives me minus 2x over x to the 4th, which gives me minus 2x to the minus 3, or I can write that as minus 2 over x cubed.
No, I thought that
Okay, so we're out of time today, but I will answer your question. But we will finish up 2.2, do more examples tomorrow, and take the quiz. So I'll see you guys tomorrow. You have a question?
Yeah. So, okay, that's what I thought.
Yeah.
So this and this do not cancel. So how did you get the H up here? You
This and this does cancel. It does cancel here. You can leave it like this and cancel it, or
You can flip it.
yeah. So
and
yeah,
times it by
when
the
you
reciprocal.
because this is h over 1, so when you flip it, you have 1 over h. So you see,
But
it's
it'll
in
still
this.
cancel
It
there,
will.
too.
It will.
Okay. So that the way I read it is mathematically correct.
Correct. Yes, it is.